It says preparing. Okay, good. That was in the steps, it said click on your email next. So that's what.
No, you're supposed to wait to click it because it's going to be streaming now.
Okay, great.
So go ahead and put up the break slides because it just sent out the email to everybody.
Okay. How do I stop? I want to stop sharing my screen. So I'm just going to leave it like it is.
Yeah, you can close out of this window.
Okay. How do I? Well, I closed out of my browser. How do I stop sharing? I guess is what I want to do. Stop
The green
sharing.
button.
Okay. That confused me. But okay, we're streaming now. Great. Well, thank you. And I will share.
Elizabeth, do you have the break
break
slides?
screen? Yeah.
I sent, yes, I sent it to him.
Yeah, go ahead and put that up because we're already streaming.
Okay.
So people don't just see us talking.
Although it's only shows the sessions that are after the break. But at least it'll be something.
Okay. I'll work on that right now.
Or actually,
It's
Todd,
okay.
just share the agenda instead so it has everything.
Okay. I'll do that then.
Thank you.
Yeah, here's a link to it. If you just download and make it full screen, that should be good. And then just do that one you had up during the break.
All right.
We're going to hop off. Just send a message if you need anything, Todd.
Okay. Thanks, everybody.
Okay, bye.
You should be able to do, Todd, if you go up to the top where it says view, I think that's
Yeah.
how you get the full screen. Yeah, there we go. See full screen mode.
Yeah.
Yeah, try that to see how that looks. All right. That looks
Okay,
good.
thanks.
All right. So I got another meeting coming up at 8:15, so I'm gonna leave the audio. But I'll hang out in here and just send me a Google chat if you need me for anything.
Okay, looks good. Thanks for your help, man.
Yep, no problem.
Good morning, everybody. I just wanted to do a quick check for later in the day when I'll be speaking to make sure that you can hear me.
Good morning, Robert.
Great. I will mute myself and turn off my camera to save bandwidth now. And I'm also seeing that I have a share screen button for when the time for my talk comes up. I hope that's good enough. Thank you.
Looks good, thanks.
Mhm.
Hey, Ryan,
Hey,
should I hit the live transcript button to turn closed captioning on?
yeah, go ahead and do that for accessibility purposes.
Thank you.
Is Frank here?
Haven't seen him yet.
I don't see Frank yet, but I'll check. He's in the office.
Todd, do you want to make me a co-host real quick in case I need to mute anybody or anything?
Mhm.
Sweet, thank you.
Somebody's got a Greek goddess type. What do you call it? Icon?
Morning, everybody. A lot of coffee drinkers here already. So we have a bit of time for our first talk. The first talk we originally scheduled had to cancel at the last minute, so we'll be starting around in about 15 minutes or so. So Ian, do you want to moderate the first couple talks?
Sure.
You look quite comfortable there.
You're in Breckenridge.
What's the temperature up in Breckenridge?
Oh, it's like 60 something right now, I think. Oh no, it's 46 right now.
Let's see. Well, Bob, I was gonna show a slide at the end, but I can bring it up. I wasn't planning to do this right off the bat, but let me just share things I was hoping to cover at the end, our final discussion, but maybe people can start thinking about them. One was, for those of you who were at the plenary yesterday, I think Julio laid out the CSM3 timeline. And so the idea is that we're doing, working quite closely, especially with the atmospheric model and sea ice folks, right now to pull together a fully coupled system that other working groups can then start working with for their testing over the next year, and that there would be some kind of a release to the community in about a year from now, whether that's called 3.0 beta or 2.x, I'm not sure. So part of the discussion today will be about setting our development path priorities towards next summer. Another thing that Ian and I need to do this summer is write our next proposal for computing time. That will cover the period 23 to 24. The new NCAR machine will be arriving supposedly in January now. they've been having trouble, I guess, procuring enough chips to build it. So we'll see what happens. And that will be a system with a substantial fraction of the nodes being GPU based. So exactly how that gets allocated, I'm not totally sure yet. But based on our prior allocations, I'm expected that our guidance will be for requesting somewhere in the range of 30 to 40 million core hours. And we typically split that about 50-50 between what's called production, which is typically science problems we wish to do as a community, versus development, which would be testing and testing of new capabilities. And then I thought we could also touch on whether there might be some opportunities, some additional opportunities for collaboration across the MOM6 community, as as we're, at least from our perspective, as we're pulling together a new system, whether there might be some opportunities for joint experimentation in a controlled multi-model kind of framework where GFDL, EMC, and CAR are doing some kind of experimentation together to understand particular aspects of sensitivities or motion processes together. So those were things I thought we might touch on. Yeah, and then we have those sort of focused discussions on process level development and implementation in the second half of this morning's session. So that's what I had, but open to other suggestions. Say that everyone has their cameras turned off. It's very early in the morning, but you're welcome to turn them on now. This is meant to be social time. You don't have to raise your hand even, just shout it out there, Bob.
Okay. So I'm curious, I know that there's a lot of work going on, especially with the CGRID version of CICE. Are there any particular difficulties with the ice-ocean coupling? I'm not seeing any discussed on the agenda, but and it may not even be something that people fully understand yet, but is that going smoothly, or is that something where there are interesting challenges that would be worth discussing in the few minutes we have here?
Well, you're certainly more informed than I am. We're not seeing any difficulties we weren't already anticipating. We're still, our coupled simulations are using the B-grid version of CICE. That I don't think is a big deal for us. We are, there's a few little bays here and there that things have gotten clogged up because the ice model has zero velocities at a channel that we thought was open and isn't really. So, so we need to do a few little tweaks to our landmass. But other than that kind of thing, I'm not seeing anything that alarms me. Dave, do you have any, from your preliminary looks, are you seeing anything?
Well, again, I think most of our focus has been on the salt, freshwater, and heat. We have not had to worry about dynamics and momentum to this point. But I think that is going to be an issue coming in the next year for sure. So, but I know this is your favorite conversation, Bob, but we are still levitating the sea ice at this point. I think we'll continue to do so for a while. But it is, again, there's a long-term thing about embodying the sea ice more physically. But for now, I think we just want to get the basic coupling of those four fluxes going.
That sounds entirely consistent with kind of our experience, especially thinking back to when we were using the B-grid version of SIS2. And the C-grid version is still a work in progress, or is that something I hear rumors to the effect that it's almost ready, or that it's
the C grid version, I think we've blessed it. It's on the main consortium branch, so anyone can download it at this point. I do not have that version coupled into CESM yet. There's still some technical challenges there, but that should be available soon. As Frank highlighted, the fact is that we're not really going to be making land mass changes at this point where a C grid is going to be beneficial necessarily. So we'll probably still couple in the B grid at least for another 6 months to a year. So
thanks for those updates.
Let's see. Good participation here for coffee time. Point out that our co-chair is actually attending from Breckenridge. Lucky him. Multitasking. Taking over our old venue. Is it nice now? Yeah.
I'm happy. Yeah, I'm enjoying it.
Yeah.
It's atmospheric talks this morning, which, not to say that I don't like atmospheric talks, but at least it's convenient.
Well, we scheduled it on purpose like this, so
Oh,
that
good.
it wouldn't match the ocean talks there. So that was the idea.
Yeah, this year there's also the Gulfstream meeting in Woods Hole this week. So there's like total traffic jam on the calendar this week.
There's also the SOCOM meeting in Princeton.
Yeah. That's in person, the second meeting?
Yeah, I think it's Wednesday, Thursday, Friday though, so.
Right. Scheduled here, see when I'm supposed to start. I guess I'm technically supposed to be starting now.
I've got it at 8:55, or you start at 8:50.
Yeah, okay, that's right.
First talk at 8:55.
It's mine.
Okay, well, good.
Yeah, I made sure everyone's here. All in the first set, everybody's logged in.
Great. Yeah. And the smoke is kind of cleared today a little bit, so that's good. Those of you who weren't in Boulder yesterday, you were lucky because it's very hot and smoky here. Seems to be the new norm for our summers.
We had a little smoke up here yesterday morning, but it cleared out pretty quick.
There's not much wind down here yesterday, so it just kind of sat here. Yeah.
Smoke in Alaska too.
Yeah.
Where's that coming from?
There's a couple big fires, one out in the Yukon Kuskokwim Delta area and others south of us. Nothing nearby.
It won't stop raining here in Seattle. It's definitely January this year. I think we're getting all the moisture and cold.
No. It looks like we might be in for a three-peat La Nina this year, which pretty amazing.
We need to check our prediction simulations to see whether it's
What
confirming.
Steve says. What's Steve on?
Tell me when this cold is going to end. Our poor tomato plants are like struggling.
Last year it was too hot. This year it's too cold. So
I know, I'm never happy.
yeah.
Well, I just realized this morning I went down to say hi to Steve, and there are 3 offices in a row down there with Distinguished Achievement Award winners. Keith Lindsay, Steve Yeager, and Peter Gent. Then we
Wow.
skipped 2 offices over to Gokon's office. So that end of the hall is quite dense and high achievers. So. So Joni and Anna Lena have a lot to live up to. They're kind of in the middle there.
Pressure.
Yep. Another second. Just ask, do we have, oh, Kaz Masumi is on. Kaz, welcome. What time is it there?
It's midnight.
Midnight. Wow. Well, welcome and thanks for staying up late.
Thank you.
Any other international participants? Let's see. Okay. Well,
There's somebody from Tsinghua University, Ximing Xu.
Oh yeah. Welcome.
Hi, it's also very late here, so I'm listening to the presentations from home.
Okay.
Sorry guys, cannot show up.
Yeah, well, welcome. Glad to have you.
Thank you.
All right.
And our graduate student, one of our recipients is here too, I think.
Oh yeah, Abigail's here. Yeah, congratulations, Abigail. And yeah, let's see. I'm just gonna say, and also just let me give a shout out to Todd Amadeo, our administrative assistant here in CGD, who's helping run the show here, and he's a key member of our group, keeping things running smoothly, and a new father. So congratulations.
Thanks, Frank. Good morning, everyone.
And for those of you watching in the middle of the night, if you do doze off, remember that everything's being recorded on YouTube, so you can catch it again tomorrow if you missed part of it. All right, so let's go ahead and.
This meeting is being recorded.
Okay, so there you go. So we're not putting the coffee hour on YouTube, I guess. That's good.
I'm going to share my screen.
Hold on a second.
Oh, okay.
Let me just run through the logistics stuff. Let me see that. Yeah. Okay. Whoops. Whoa. Yeah. So here we are. Welcome everybody. Just give you an idea of the agenda. We will. I've got it on auto here. I have a few science talks this morning. First, in the first part of the meeting. Then we'll go into some of the recent work here at NCAR with MOM6 development, both regional models and global models. And then we're going to try something a little bit different for our working group. We're sort of solicited talks on process representation in MOM 6. First on mesoscale, submesoscale processes, and Scott Bachman and Ian Grooms will sort of lead that part of the discussion, and we'll leave some time to address those kind of issues and how we can advance that science through CESM and how we should be pursuing our development path in those directions. And then similarly for diapycnal mixing processes, and Bob Hallberg and Ali Mashaek have agreed to lead that part of the discussion. And then we have some time towards the end there for some open discussion about the working group plans and priorities over the next year or so. So that's the plan for today. Just the logistics here. Usual Zoom etiquette. Please stay muted and turn your camera off while others are presenting. If you have a question during the talk, please put it in the chat and we'll address it. And then after the talk is completed, feel free to turn your camera back on during the discussion, and we'll try to use the raise hand function to take turns and take questions in turn. And finally, just to remind everyone of our values here, to promote constructive scientific discourse. So please, during the discussion, offer constructive feedback, share the error, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. So with that, we'll go to our first talk, and I guess I'll turn it over to Ian to moderate this first couple talks. So go ahead, Ian.
Thanks, Frank. Our first talk is Rosa Shu, and feel free to share screen. We have 20-minute slots, so some of that is for your talk and some of it is for discussion, but I'll try to cut it off at 20 minutes so that we can stay on track. Rosa, are you ready?
Yes. Do you see my cursor moving?
Yes.
Okay, cool. Awesome.
All right, go ahead.
Okay, I'll get started. Good morning, everyone. Welcome to the first talk. And for this talk, I'm going to share with you my research about how the ENSOs affect the ENSO statistics. And I am a graduate student at Brown University, and I finished this project with my advisors, Professor Zheng Li and Professor Bela Fox-Kemper. And we collaborated with Dr. Ian Planton and Dr. Michael Maffaden from NOAA PMEL. So firstly, just to remind you what is ENSO, it is the interannual variations happening in the eastern coast of the tropical Pacific. During El Nino, there is abnormal warm in the eastern coast, and then during La Nina, there is abnormal cold here. But the impact from ENSO does not restrict in this local area. The impacts can be transferred to different continents of the world. And so the ENSO variations has a global impact. For example, during the La Nina in 2021 to 2022, there was severe droughts in Sydney, Australia. And on the contrary, in California, there is a normal drought here. So it is important for us to understand the ENSO cycle, but we've encountered some challenges to understand the tropical Pacific climate. And the first challenge, oh, sorry, the figure does not show up here. Oh, I'm so sorry. I don't know what's going on.
Maybe go to full screen and see if that works.
It works yesterday, but Can we move on to the second talk first? I will try to fix this problem as soon as possible.
Ooh. I don't, Frank, do you want to try something like that?
Is this a problem throughout the talk, or is it just one figure?
They are important figures.
Yeah, there's a lot of missing slides.
Okay.
Yeah, sorry.
Yeah, we can. I'm okay with that if the second speaker is ready.
I'm sorry.
That's okay.
Okay, so Giovanni, are you willing to jump in on short notice? I think you're
absolutely. Yes. Oh, sorry.
Oh, sorry. No, Giovanni is third. I'm sorry.
Okay.
Lili is
Yeah.
next.
Okay, I can go ahead. Can you see my screen?
Yes.
So.
Okay, it's in presentation mode.
Yes.
All right. Go ahead. Thank you.
Okay, thank you. Okay. I'm Lili Ju from University of South Carolina. So maybe different from most people here, I'm a mathematician working on numerical method for partial differential equations. So today I'm going to talk about some numerical method for the ocean models. And of course, I thank the organizer for giving me the chance to present some of my recent works. So the title here is we call the high order multirate explicit time stepping scheme for the baroclinic-barotropic split dynamics in the primitive equation. So this is a joint work with my postdoc, Rihui Lan, and my colleague Zhu Wang, and the Professor Max Gansberg from Florida State, and Phil Jones from Los Alamos. So I will first introduce what the primitive equation we're going to talk about, and the stratification effect. You get the layer, the primitive equations. What is the dynamic splitting and the spatial degradations? Then we're talking about the high order split time stepping scheme based on the framework of strong stability preserving longitudinal method, and what we can do to use multirate in the SAPRK framework to achieve high order. Then finally, we present some numerical experiments to demonstrate the performance of our schemes. So this is a primitive equations. Okay, usually it's the incompressible Bosniak approximation under the hydrostatic balance. Okay, so you have the thickness equation. That's from the Wallen conservation. You have momentum equation. Also, you have some tracer equations. For example, the potential temperature and the salinity. Also, you have the hydrostatic condition and the equation of state. So these are some notations. So we present here. Here the U, is mean the horizontal velocity. W is the vertical velocity. H is a flow thickness. In fact, you have to understand in a spatial way. Okay, and then to consider the stratification effect, so we partition the fluid into air layers. Then some variables you have to put in each layer. For example, the horizontal velocity, UK, the layer thickness, HK, and the tracer variables, 5K, you have put in the middle of each layer, but the vertical velocity put in the top. And the interfacial height you defined from the bottom, the capital H, the total column height at rest, then you add back each. So the top sea surface level will be the Z0, okay? So that's the basic idea. What is the multi-layer shallow water equation? Here is you just apply some central difference scheme along the Z directions. So here I highlight in red that you discretize all the operators in Z direction. Okay, in horizontal direction still is continuous. Okay, so you get the multi-layer that's defined for each layer, L layers and K equals 1 to L. Okay. Then what is the dynamic splitting? So the baroclinic-barotropic. In fact, because in each layer you have horizontal velocity called UK, okay? Then the first mode is a two-dimensional barotropic mode. It's weighted, flow thickness weighted average of the velocity. And of course, the baroclinic is just, for each layer, you subtract that from the original velocity UK. So you can regard it as some kind of mathematically, you can regard it as kind of a perturbation. Okay. So here, so for this, you know, for the fast mode is only one layer or just 2D. Okay. For the slow mode, it's a 3D because you have k layers along the z directions. For the baroclinic mode, important things is remember it use the flow thickness to weight it, then the weighted average is 0. So then you get the split system. You get a solid baroclinic mode, the equation 12a. Okay, here look at this G bar. Okay, and the barotropic mode 12b. Here the U bar, right? U bar is the barotropic velocity, but here you have to introduce the theta. Theta is the surface height perturbation. Okay, also the flow thickness equation, the three systems. Here, what's the G bar? In fact, the G bar is including all other terms. Okay, it's hard to be represented explicitly. You just think the effect, the forcing G bar is make the weighted average of the baroclinic velocity to be 0. That's in fact is the mathematical point of view of this effect. Then, okay, you do the spatial declaration because we only did the vertical. Now you do the spatial, just use the orthogonal dual mesh. That's currently used the M-Path Ocean or E3SM. In fact, our project is partially supported by the E3SM project program. Okay, so you do the global ocean titularizations. You get this dual mesh, then you do the finite volume titularization. In fact, the trick is a C-grid stuttering. Okay, you do the discrete divergence gradient and the curve operator by finite volume titularizations. Of course, also there's some reconstruction operator you need it, okay, to get this tree scheme. So that's not our focus. Our focus is after such a titularization, you get the spatially discrete systems. Now that's called a system of ODEs, okay? So now the time, how to do the time integration? So suppose we have a partial V, partial T equals FV. FV is the flux, okay? Then remember this famous strong stability preserving equation. It's a convex combination of forward Eulers. Why we use this one? I will explain later. So forward Euler is from first one, from Tn to the Tn plus 1. What is SAP-RK2? The two stage is two forward Euler, then do average. That means from Tn to Tn plus 1, Tn plus 1 to Tn plus 2, then put the average result at Tn and Tn plus 2. So also you have SAP-RK3. It's a convex combination of 3 forward Euler time steppings. Okay, so then you get here is you solve the baroclinic mode. You use the forward Euler. Okay, suppose from T0 to T1, T0 is current time. Then you can. Its basic idea is what? How to compute the G bar. G bar, remember, make a weighted average baroclinic mode to be 0. So I first forward the baroclinic system without the G bar term. Then I compute what kind of G bar to make the weighted average of the predicted baroclinic mode to be 0. That's from the idea of Hickton 2005. So here the G bar just can as a first order approximation of the true forcing at the current time steps. Then because this is forward Euler, so I can do a combination, a convex combination forward Euler based on the SAP-RK framework to get high order schemes. Here also is a vertical mixing I want to mention here. Vertical mixing is the rate term, in fact, is vertical diffusion. Okay, people say, okay, sometimes for numerical stability, want to separate this one. Okay, so you solve the other term explicitly, then do the vertical mixing. Vertical mixing because it's only vertical direction. So they are in the totally parallel for all the vertical directions. So that's meaning you can use a tridiagonal solver to get a quick solution. The IMAX scheme, in fact, is a IMAX scheme. In fact, also is just first order IMAX schemes. So the trouble is sometimes it does not fit into the SAP-RK framework. Okay, so then that's meaning we use delta T to forward the slow mode, the baroclinic mode. For the faster mode at each stage, you have to use the substepping here. If the delta T is large time step size, then delta T over M. M is the substepping. Okay, so you use small time step size for each step. And then we can get this SAP-RK2 split multirate schemes. The idea is what? okay, first you do the pre-processing, you do the decomposition. Okay, you have velocity at each time, you know current velocity. You do the decomposition, get the U bar n and the U tilde n. U bar n is the fast mode, U tilde n is the slow mode, but one is 2D, one is 3D. Okay, then what do? You use .rt to advance the splitting system. So basically, you see the 13A, you advance the baroclinic mode by forward Euler. Okay, at the same time, you get a G bar N0. Okay, that's the forcing, a first order approximation forcing. You get a predicted baroclinic velocity at the Tn+1. But to get a high order, you need to go on, right? But to go on the baroclinic mode, you have to use assistance from the flow thickness and the barotropic mode. So you have to do 13B, 13C, 13D, and E. What do you mean? You compute the barotropic mode, you substepping. Okay, then combine together data predicted velocity at Tn+1, then you can update the flow thickness and the sea surface height perturbation. That first stage is done. Okay, then you do the second stage for baroclinic, because now the baroclinic, you can do the forward Euler from Tn+1 to Tn+2. So you get a prediction at the Tn+2. Also, you get G bar N1. That's another forcing for the second step. Okay, so this is then the baroclinic is done because you get a prediction at Tn+1 based on the SAP RK framework. You can do an average, get the true update at Tn+1, so you get 14B. Then what do we do for barotropic mode and the flow thickness? So barotropic mode, you say, can I go ahead and update it? Then you don't get high order because each step is for the barotropic mode is substepping. It does not fit to the SAP RK framework to get high order. You have to use the 14A, substepping from Tn to Tn+1. But what is the forcing? The forcing now it becomes the average of G bar N0 and G bar N1. Otherwise, you lost the high order. After this one done, then you recover the update, get the updated velocity at the Tn+1. Then you update the H, the flow thickness, and the sea surface height perturbation theta. That's the idea. Similar things. So you can do the SAP RK3 scheme. You can do the update here, right? For each one, so similar idea. You get each first pre-processing with current velocity to the splitting, then update the baroclinic mode. Okay, stage 1, stage 2, stage 3. Okay, you use substepping for the barotropic velocity, but the large time step RT for baroclinic. But in order to get high order baroclinic, you can compute at each stage. You get a prediction G bar N0, G bar N1, and the G bar N1/2. Okay, so the barotropic only for systems now is not true update. So after that is done, then you use the true forcing combination. The interpolation here, I write down the red part. That's each stage. You get what is the true forcing. Then you update, then use to correct the barotropic mode. Otherwise, you lose the accuracy. Then you update the flow thickness and the sea surface height perturbation. So we think, okay, is that enough? The idea, I get SPRK2, SPRK3. So I hope, because we saw the fast mode always use the small time step, the slow mode is a large time step. But unfortunately, remember here, the sea surface height perturbation can be determined from what? From the barotropic subsystem, so the barotropic subsystem. Also, you can get from the update of flow thickness. So in the PDE level, they're the same, but in the fully discrete level, it's overdetermined. For this algorithm right now, it's always determined from update of the flow thickness. But you are substepping for the barotropic solver. Are they consistent? If they are not consistent, then your mode solver are still tangled together. You don't have the stability. So you want to keep the accuracy, you want the stability, you have to carefully. Be careful here. The idea is here, we thought one idea is reconcile the sea surface height perturbation. So the idea is for SPRK2, how do you can reconcile the sea surface perturbation is, okay, there are two substepping, there are two updates for the flow thickness. You just check for each one, what is the flux, okay? The flux for the barotropic substepping, the flux for flow thickness update. Okay, you take difference on difference of their flux. Then you, based on the weight, the flow thickness of each layer, you design so-called transport velocity adjustment and to make up the difference. So that's the idea here. Then, okay, no matter what, you use the flow thickness, layer thickness, or use the barotropic solve, you get same results for the system head perturbation zeta. Okay, same things for the third order scheme. So idea here, you can, of course, there are 3 stages. You have to compare, then you update our original algorithm. Then our numerical shows is then become very stable. Okay, so we use the baroclinic channel test case. Here is large Eddy simulation. Okay, so we use 20 vertical layers, and the horizontal mesh is 10 kilometer resolution SCVT mesh. And for this example, the vertical mixing vertical mixing has no effect in this test. In fact, we numerically also verify it. And we use, because there's no exact solution to verify the convergence order, so we use a very small time step as a benchmark solution. We find this C-surface head reconciliation is very useful for stability and accuracy when the substepping is large. Also, we find, based on this framework, SAP RK3 SE still does not recover the full third order accuracy. Okay, what's the motivation for our work is here, because we use the current split approach in the MPath ocean. We do the benchmark test for time accuracy. We find, in fact, it's at most first order accuracy. Okay, it's stable, but it does not follow some mathematical principle for designing high order scheme. In fact, it does not give you high order accuracy in time. Okay, and for this work, you can see here, no vertical mixing is applied to this baroclinic channel test case. The left-hand side, no C-surface head reconciliation, and the right one is C-surface head perturbation. You can see with the C-surface reconciliation is much stabler than the other one. Also, we find for long-time simulation, it's become more stable. Okay, this one is SAP RK2, and we can get perfect second order schemes. Of course, 1M is very large because the inconsistency, the error term for the fast mode, slow mode is highly imbalanced. So it affects the overall time accuracy a little bit. Okay, but it's not that big. You can see you get a perfect convergence. Okay, that's get high order accuracy. For SAP RK3, you look at here, the left-hand side without SSH reconciliation, we only get a second order. And with SSH reconciliation, we get still not a little bit better than second order, but still not third order. In fact, if you go back to the numerical scheme, you see there's still some violation of the SSPRK framework. That's why the truncation error, in our paper, you can see our paper, the truncation error analysis show it cannot give you third order, but at least second order. Then why? What's the benefit of SAP RK3? It has better stability and better accuracy. Okay, so we did some simulations. That's we used the M equals 16. That's meaning the time step for the barotropic is 15 seconds, for the baroclinic of 240 seconds. Okay, and we compared. So we also couple with the tracer solver in the MPath ocean. Now we can see that the high order scheme does play an important role. That's a comparison with current MPath split EXP scheme. The absolute difference keep increasing along the time, with even different drag coefficients for the bottom. Okay, so we want to see you have to do high order. Then also do the global ocean test. This one, of course, is not a Laplacian. It's a biharmonic operator for stabilizations, and we observe almost similar behaviors. Okay, for this one, vertical, we know SH reconciliation is important, so we always apply it. Without vertical mixing and with vertical mixing, for the global ocean seems to have some difference. And we show second order, you can get a second. But after apply the vertical mixing, like I analyzed before, in fact, it's the first order MX scheme. It does not fit the SSP framework. Sometimes, if it's very influential. Like here, we reduce to the first order. If you add vertical mixing, maybe it's more stable, but the accuracy will drop. Okay. For SAP RK3, it's same things. Okay. Without vertical mixing, it's high order, but vertical mixing, it dropped to first order. Okay. So I want to say here, the vertical mixing is stabilized, but it will destroy your accuracy. Okay. Also, we compare with current tracer solvers. We get the left one is the potential temperature evolution. The right one is the surface salinity difference. Okay, that's the difference, not the true value. The difference with the MPath SE. I want to show the high order accuracy importance. Also, we did the performance test. So we use different substepping. We can see use better substepping, of course, you get almost the linear speed up time efficiencies. Okay, of course, here the 3D barotropic solve always dominate the computational cost. That's in the query with 64 cores. So here is how to some remaining work, how to recover SPRK3 scheme, third order. Also for vertical mixing, can you get high order vertical mixing? Not the current popularly used in ocean modeling. Also, how to do the try high order tracer solve coupled to the dynamics. Also, can we do, because still the error is imbalanced for the barotropic baroclinic model as long as you use multirate. Can we use implicit solve, but still high order accurate for the faster mode? So the sequence of works. And if you're interested, please refer. I refer to our work in JCP. And thanks to the support for the BER and the ASCR in the part of the E3SM project. Thank you.
Thank you, Lili. So we've only got about 20 seconds. So instead of having questions, I think I'm just going to try and get the next talk set up. But if there are questions for Lili, we do have a break at 10:15 and we can maybe discuss then. So let me come back to Rosa. Do you think you're ready to go yet?
Yes, I exported to the PDF version, so to make sure it works.
Okay, let's give it a try then.
Yeah. So I'll catch up from here.
Yes, this is the one that didn't work, I recall.
Yes, exactly. So just to remind you, my research is about the ENSO, and then I'll jump to the introduction of the challenges that we are facing in simulating the tropical Pacific climate. And this figure shows the CESM model's bias in precipitation surface temperature. And I think this is for CSM1. So the error it is having that is outstanding from this figure is that the precipitation is overestimated, especially in the central South Pacific region. And for sea surface temperature, it is simulating an excessive warm pool in this eastern coast region. Aside from the biases in the background climate, there are also biases in ENSO variations across a lot of climate models. So the errors include in the aspect of amplitude and frequency. The left figure shows you different model simulation for ENSO amplitude, and this column is the observation data. You can see that there are many models that disagree on the amplitude of ENSO variations. And the right figure is the frequency spectrum of the ENSO variation. This very thick black line is the observations frequency, but a lot of models are having some strange peaks in the spectrum, which does not appear in the observations. So since we have these challenges in both the background climate and the ENSO variations, one question that we may ask is what is going wrong in these climate models? Inspired by Takahashi's research in 2007, he thinks that the Andes is an important factor for the formation of the Eastern Pacific climate because it can modulate the westerly wind from the mid-latitude Pacific and force it to turn towards the equator. Therefore, we think that the error in the tropical Pacific climate simulation might be originated from the error in the representation of the Andes. So this figure shows you the South American topography. The left figure is the high resolution satellite data, and the right figure is the CESM model's representation of the topography with the resolution of about 2 degrees. You can see that the Andes is a very tall and thin mountain range with its highest elevation of above 5 kilometers. But with the smoothing in the low resolution global climate models, even the highest elevation here is not as high as 3 kilometers. So we think that the climate models are not capturing the effective height of the Andes. Therefore, we did an experiment of elevating the height of the Andes. We changed the mountain elevation along the grid cells for the mountain, for the Andes mountain range, and and change it to the maximum height according to the high resolution satellite data. And then we call this experiment the higher Andes experiment. And we run the global fully coupled model together with this default elevation to see how the climate simulations are changing. We used the CESM 1.2.2 fully coupled model with the horizontal resolution of 2.5 degrees times 1.9 degrees. We used the component set of B2000, which means the CO2 forcing is as in 2000, so that we can compare our model result with the observation data. Because this is a fully coupled model, we will expect the model take a relatively long time to catch up with a relative equilibrium with the upper ocean. So we run the model for 350 years, and we use the last 160 years of data for our analysis. Firstly, I'm going to show you the result for the background climate. This is the sea surface temperature distribution for meridianal and zonal directions. You can see that in the control simulation, it is simulating a higher sea surface temperature across the whole tropical Pacific. And when we increase the height of the Andes, we not only lower the sea surface temperature across the Pacific, but we also increase the north-south sea surface temperature gradient, which is more consistent with the observation. And for the zonal distribution, it is similar. The higher Andes experiment is lowering the sea surface temperature, especially in the eastern tropical Pacific. Therefore, it increases the east-west sea surface temperature gradient as well. Secondly, we also look at the surface wind stress curl, which is consistent with the which can be influenced by the temperature and can influence temperature, vice versa. So this is the zonal wind stress curl in its zonal distribution. One thing I want to highlight here is that in the eastern tropical Pacific, the wind is actually getting weaker because this is the zonal wind. So the negative number means it blows towards the west. And when the absolute value is larger, it means that the wind is stronger. So in the eastern tropical Pacific, we are seeing a weaker zonal wind stress in the higher Andes case. But in the central and western Pacific, the zonal wind is stronger here. And the other factor I want to highlight here is the meridional wind distribution in the meridional direction. And if we look at the equator, you can see that the wind is actually blowing from the southern hemisphere towards the northern hemisphere. And if we increase the height of the Andes, this southerly wind is getting stronger, which means that the hemisphere's difference between the northern and southern is getting stronger in this higher Andes simulation. And since this is an ocean group meeting, I also want to show you the upper ocean vertical temperature distribution here. This is the temperature distribution in the Nino 3 region, which is a box in the Eastern Pacific region. One thing you can see here is that for the higher Andes experiment, it is showing a smaller vertical temperature gradient, and it is more consistent with the observation. It means that when we change the height of the Andes, the upper ocean is getting less stratified here. So these three changes are what we observe in the background climate. And since we've changed some properties in the background climate, we are expecting some changes in ENSO variations as well. And here's what I'm going to show you. Firstly, the most impressive result that we get is that when we increase the height of the Andes, the amplitude of ENSO variation is getting much weaker than the control simulation. The left figure is the zonal distribution of the sea surface temperature anomaly standard deviation. It can represent the strength of the ENSO variations here. You can see that in the control run, it is simulating a much stronger variation, especially in Central and Eastern Pacific. But when we increase the height of the Andes, it is capturing an approximately same amplitude as what we've seen in the observation. And this result can also be shown in the probability distribution function of the Nino 3 index. Because the control run is simulating a much stronger variation, we are observing a lot more strong El Nino and extreme La Nina events in the control simulation. But when we increase the height of the Andes, it is showing a similar PDF as in the observations. Second aspect that we are looking into is the frequency spectrum. You can see here, there is a very strong peak in the control simulation with around 5-year cycle, which means that in the control run, the ENSO is happening very regularly with around 5-year cycle, which is not true in the observation data because it does not see a very strong peak in this frequency. And when we increase the height of the Andes, the frequency spectrum gets more similar to the observation again, with no such an outstanding peak at a specific frequency. The last aspect we are looking at is the symmetry between El Nino and La Nina. We use skewness to quantify the asymmetry here. So if skewness is positive, it means that there are strong and less frequent El Nino compared with La Nina, which is true for the observation. And the observation is seeing a skewness of 0.94. And if this value is getting larger, it means that the asymmetry is larger. But when we look at the time series of the Nino 3 index in the control simulation, we only see a skewness of 0.43, which means that El Nino and La Nina are very similar to each other. But in the higher Andes run, the skewness gets improved to 0.7, which means that we are improving the simulation of the asymmetry between the positive and negative phases. So one question you may ask is, why does these changes happen? What process has the higher Andes experiment changed? To quantify the process, we are following the research done by Zhao and Fedorov in 2020. We're using the Biernes Stability Index to quantify the feedback strength for the ENSO cycle. So the BJ index can be separated into 5 terms. The thermal damping term, which quantifies the surface latent heat, sensible heat, shortwave and longwave radiations. The second is the mean advection damping. It consisted of the zonal advection, the meridianal advection, and the vertical advection. And these 3 are the mean advections damping. And the last 3 terms are the positive feedbacks. They are the zonal advection feedback, Bachman feedback, and thermocline feedbacks. They are quantifying the anomalies sensitivity to our changes. So overall, what we've seen here is that when we calculated all these terms in the higher Andes experiment, the BJ index is having a stronger damping effect to the ENSO cycle, which makes the ENSO variations weaker than the control experiment. And for this stronger damping effect, it is mainly contributed by the stronger thermal damping, the stronger mean advection damping, and the weaker thermocline feedback here. So to summary, our research shows that the higher Andes experiment can improve the tropical Pacific climate simulation, both in the background state and in the ENSO variations. And we proved that from the mechanism part, it is having a weaker ENSO cycle because the higher Andes experiment is having a stronger damping effect from the BJ index. That's the end of my presentation. I'm happy to answer questions.
Thank you, Rosa. I see that Justin has his hand up. Justin, do you have a question?
I do. Yeah, so I also wondered about horizontal resolution. If there's been some simulations done with higher resolution. And I wondered if you'd looked into whether the effect might be similar if you make higher resolution.
Yes, I've seen a paper that is using a regional climate model to see if the resolution of the Andes is having an impact on the tropical Pacific Ocean. And the result shows that for the higher resolution Andes, it does simulate a better sea surface temperature distribution, especially in the eastern Pacific. But because their research is for a regional climate model, they cannot simulate the complete ENSO cycles, so they did not look into this aspect. And I think the high resolution definitely improve the simulations there. But one question that you may ask is how high the resolution is enough for correctly capturing the effective effect of the Andes. Yeah.
Yeah, well, thank you. I think there have been some global high resolution runs done. I can send you some links. Thank you.
Cool. Thank you.
All right, I'm going to go next to Shiming Shu. Hope I've pronounced that correctly.
Thank you. So I wonder whether, the slab ocean setting has any effect on your results.
Oh, sorry. I need to share it again. I thought it was okay.
So you're running slab ocean, right?
No, this is a fully coupled.
Fully coupled. Okay. Yeah. Okay.
Yeah, but we definitely also our first paper is the slab ocean model simulation. So I also have the result from the slab ocean and the fully coupled model. One similar conclusion is that they both increase the accuracy of the simulation. But the difference between the slab ocean and fully coupled model here that we captured is that the range that the slab ocean model actually changes is larger than what the fully coupled model actually changes. So we think the dynamic ocean circulation is slightly offsetting some effects from the Andes.
Okay, because we run a 1 degree model, we did the same thing, but changed the topography to a half degree. So which in effect increased the height of Andes. So that's had the same results on the ENSO, but had different results on SST because we have a larger SST bias in this region at 1 degree. That's what we have observed. Yeah.
Cool. Thank you.
Thank you. Yeah.
All right, I think we have time to go to Gokhan and then Liz Maroon after that.
Yeah, I was just wondering whether, the atmospheric models do not necessarily represent the sea level at 0 meters, right? So the it can be represented as quite a deep surface. Do you think that the representation of the actual surface height will make a comparable difference in the or on its impacts on ENSO?
You mean the actual surface height of the Andes?
No. Sea level in an atmospheric model is not necessarily at 0. It's going to depend on the discretization and the dynamical core used, but it can essentially dip down to, I don't know, minus 200 or 300 meters. Can that have an impact on representation of ENSO?
Oh, that's an interesting question. We haven't actually thought about it in this aspect first, but I think I'll think about it later. Thank you very much for the suggestion.
Liz, do you still have a question?
I still have a quick question. Thanks for the nice talk. So I was wondering if you'd looked into any of the more energetic related dynamics or diagnostics, sorry. So for example, when you raise the Andes, you're also going to be impacting subtropical clouds and where the ITCZ is. And that could also have another way of analyzing what could be going on, how ENSO could be changing through cloud diagnostics. So I was wondering if you've taken that angle yet or not.
Yes, actually, this is the second step of experiment that we are doing in a fully coupled model. And before this one, we run a similar simulation in the slab ocean model, which we focus more on the change in the atmosphere circulation and clouds feedback. And what we've seen is that because the sea surface temperature is decreasing in the Southeast Pacific cold town, and this decrease of temperature is having different reasons from off coast and like near coast region. So near the coastal region of South America, we see a lot more low level clouds. So it's blocking more solar radiation. So this is the reason the sea surface temperature is decreasing in the coastal region. And for the off-sea region, because we modulated the atmosphere circulation, so the southeasterly wind is getting stronger and induces more evaporation. So the central Pacific region is actually cooled by evaporative cooling. Yeah. Thank you.
All right. Thank you again, Rosa. We're going to go on next to, I think, Giovanni. Yep, Giovanni. And we are a couple minutes off. I've allowed us to get a couple minutes off because of the technical difficulties, but I'm going to give, everyone's going to get their 20 minutes. So, Giovanni, if you want to share screen.
Yep. Here we go. Yeah, so on the time comment, my presentation, the most shorter side, because it's more of an update. So I'll be happy to, give some time to questions for Lili or whatever the Ian would like to do.
Okay.
But yeah, thank you for having me. My name's Giovanni. I'm a PhD student in Atmospheric and Oceanic Sciences at CU Boulder. And I'm also a graduate visitor through the ASP program at NCAR, working with Gustavo Marques and Frank Bryan. My advisor is Donato Giglio. We've been working the last few months on setting up a regional MUM6 CSM configuration of the Caribbean Sea as part of my thesis work, which, without going into too many details, has two main goals. The first one being examining upper ocean mechanisms driving salinity variability in the Caribbean Sea, and then hopefully using the regional configuration to understand any future changes in salinity variability in the Caribbean Sea. So with that in mind, we first started off with what we call a test configuration. It's a 1/4 degree grid of the Caribbean Sea that you can see here. Our open boundary and initial conditions were taken from the Glottis reanalysis from the European Union. Radiative forcing from JRA, runoff is from the World Ocean Atlas, tides from Topex Poseidon, chlorophyll is from seaweeds, and we're using 65 sea star vertical levels. And this configuration serves as a way to first learn how to configure MUM6 and CSM regionally properly, make sure that it's working correctly, and for us to be able to establish a good framework and workflow for this configuration in order to move forward with an actual working configuration that we can use in the future. And so we actually just finished running a 15-year presentation, simulation just last week. And this is what you're seeing here. It's color contours are sea surface salinity. The black line contours are sea surface height. We ran for 15 years from 2000 to the end of 2014. And at least qualitatively, we haven't seen anything weird going on. We can see the Amazon River plume, and that kind of highlights the retroflexion very nicely. We can see that the plume enters the Caribbean roughly through the passages and latitudes that it usually does. We can see the Gulf Stream and some eddy shedding. And so, again, as I mentioned, this run was just finished last Friday, so we haven't done any much of in the quantitative way, but at least qualitatively, it gives us a good idea of what the model's doing, and we don't see anything odd going on. So it reassures that our efforts are going in the right direction. I did a quick comparison just yesterday, just looking, comparing some Argo-weighted data from the Romick and Gilson product. Top left panel, salinity in a box just east of the Lesser Antilles. which seems to be doing rather good, anomalies and the monthly mean for the full-time period. One thing that I noticed that's very good that we're capturing, because again, we're interested in salinity, is that minimum in 2009 right here that the model captures, which is associated with the 2008 to 2009 La Nina, which resulted in large negative salinity anomalies in the whole Caribbean. So the model captures that very nicely, which is promising. And temperature seems to be doing fairly well, much better than salinity, I would say, at least, again, qualitatively speaking. Moving forward, we have a few other benchmarks just for peace of mind. And this is just to mention a few. Comparing the model to a full gridded output, like a Glottis reanalysis or some other product that may provide better information than the Argo gridded product, because we know that the Caribbean, there's not that many Argo floats, so the observations are a little bit limited on that side. Mixed layer depth comparisons, transport estimate to the Eastern Caribbean Sea from the Atlantic, which may prove a little bit tricky because at a quarter of degree, we don't capture all the islands on that side, but we can get an idea at least that the transport estimates are fairly sensible. Some EKE maps and estimates and some benchmarking of the loop current, the eddy shedding, frequency, northward extension, and so on. As this is part of the reason we wanted to work on this test configuration is that we wanted to set up a GitHub repository too, so that people can go in, follow our instructions on our work frame to configure our a clone of our test configuration, but also use the same framework so that people can create their own configuration following our workflow. And this is something that Gustavo and I have been working on and will be available at some point in the near future. And we'll make sure to send an email to the working group so that everybody that's interested in this can follow our workflow and hopefully configure some really cool regional CSM and MOM6 configurations. So we know that we can run MOM6 and CSM in a regional configuration. So what we want to do moving forward, we want to create a 1/12 of a degree grid, same extent as the quarter of a degree. And then we're going to change our initial conditions or forcing a runoff to the CSM large ensemble, particularly the more members, which have very detailed outputs fields. These are 10 members of the large ensemble, and we're going to be using that to run the model and project into the future so that we can assess any salinity variability changes in the future for the Caribbean Sea. And then, yeah, I need to highlight James Sinkins and Enrique Kirchitzer at Rutgers. They've been super helpful with helping with the whole workflow and setting up the model. And of course, the ISP Grad Visitors Program. And as I mentioned, this was on the much shorter side of the talks today. So I'll be happy to, if anybody has any questions, to answer them and then give some of my time to some of the other speakers.
Thanks, Giovanni. Yep. We do have a question. It looks like Peter Jen has his hand up.
Yes, so thanks for the talk. How do you specify the boundary conditions at the open ocean boundaries in these simulations?
So we're getting them from Glottis. What exactly do you mean from specifying them?
So how do you specify the temperature salinity distributions and what you do about inflow or outflow at the open boundaries?
Yeah, so it's the open boundaries are daily temperature and salinity and sea surface height from that we're getting from Gloris. It's just the north and east segments of the map. And then Gustavo may chime in into the second part of the question because he was the one that finished this configuration run. I don't know if Gustavo's.
We are using the flatter and Orlansky boundary conditions. So the flatter for sea surface height and barotropic velocity, and then the Orlansky for the two-dimensional velocity. Yeah, and then I think that's it. I'm not entirely sure for TNS what the option is, but I can look really quick.
Gustavo, should we move to the next question or?
Yeah, you can go to the next question. I'll look it up in the meantime.
Okay, we'll come back to you. So Steve Griffiths, are you ready?
Yeah, thanks for the talk. I want to encourage you to do what you said you'll do insofar as documenting this configuration. We were just having a chat yesterday at lunch in Princeton and commenting that to open up MOM6 to general usage, it really would be valuable to have more very detailed configuration documentation, how you actually built the model and set it up and run it and all the data sets and everything. So I know that's a lot of work, but it sounds like that's something that you want to do, and just make it happen would be really great. I'm going to put into the chat something that you can maybe aspire toward. It's a project that the NEMO community has done for some region off the west coast of the US. And it's an amazing documentation of that project. It's something that, you know, could be something to maybe emulate a bit. Anyway, good luck and thanks for that.
Thank you. Thank you for the comment. And yeah, I think this is really important for, you know, the development of the model and the community. And, you know, I've benefited from a few GitHub repos that are very detailed, whether from Enrique's group, GFDL. So kind of like paying it forward, and hopefully people can use it, whether it is to just replicate what we're doing or just create their own configuration. So appreciate the comment.
Yeah, just looks like we're doing nudging for TNS. I'm not entirely 100% sure. I need still learning about this regional configuration, but that, you know, quick look here, that's what I see.
Thanks, Gustavo. So Lili did indicate to me that he's willing to take questions about his talk now in the few extra minutes that we have here. If you recall, his talk was multi-rate explicit time steppers for the barotropic baroclinic split. Short notice, so I have a question actually about that. You may have touched on it at the end of your slides, but if you go to very large M, so you have lots of fast steps before baroclinic step, and then very high resolution in a global model, say, then you end up doing a lot of communication, and this can potentially really slow down your throughput. Did you experience that, or do you have any comments about that? Oh, you're muted. Sorry.
Sorry. I just say yes. You are right about that. Since, you know, for that test is we fixed the time step size for the fast mode. We fix that. Then use larger M doesn't mean use larger time step for the baroclinic mode. So use larger, but for that's a global ocean test. For that case, you have 100 layers vertically. So, and you get larger mesh, use fixed number of cores. So larger mesh doesn't mean each core has more computation. Then you can see for larger mesh, the efficiency get better and better. Of course, if your mesh is too small, you know, for each core, the computation cost maybe affect a lot by the communications. But when you increase scale, we don't see much. Also for that global ocean test, we see the baroclinic solve really dominate the overall cost. That's why you can see good scalings when you increase the number of substepping.
Thank you. Bob, you have a question?
Yeah, I do. So you're using a third order Runge-Kutta, as I understand it.
You shouldn't say third order Longokuta is a spatial called a strong stability preserving Longokuta. That's especially as a convex combination of forward Euler. Not general Longokuta has such a properties.
So the question though, as I understand it, your barotropic solver is having to traverse things 3 times to get that higher order accuracy. Is that correct? I know in MOM6, we use a quasi second order Runge-Kutta so that we only have to traverse things twice. Other schemes, higher order schemes, like some that Sasha Shepetkin have used based on Adams-Bashforth, tried to traverse things only once. But that added third traversal, as I understand it, is what you need to get the higher order accuracy with a kind of a Runge-Kutta family. In other words, start from a well-defined state, no past tendencies, which is absolutely critical for an Ale model. Do you see any way to avoid having to do 3 full traversals?
Very good questions. Very good questions here. So from a numerical point of view, if you want to reach the third order, that's more like a multi-step. For the Longokuta, it's just single step with multi-stages. Okay, so that's the difference here. So it's self-start. You don't need any, initially need some other help to start it. So when we try to say how, because for this splitting dynamics, the first mode is only 2D. So you really want to use small, you can use small time step, but doesn't use much computational cost. But the barotropic is 3D. You really have to use large time step. Now, within the framework of Longokuta, how you design, okay, one mode is large time steps, one mode is small time. How do you design a scheme in that framework? You get overall high order. That's the tricky questions. That's why we test the current multirate, called M+SE, no more than first order accurate. We use benchmark test to verify that. That's why we say the idea of the question is they use many kind of prediction correction, but when you check the truncation error, it's first order. It's stable, but only give you first order.
Okay,
that's what I want to say. So
the three passes of the barotropic solver versus 2. Do you see a way to avoid the third pass?
Yeah, we have to do 3 passes. That's true. That's true. Okay, but I want to say things is because the use of different time step, how to design a high order scheme is really a mathematical questions. Not that trivial. Say, okay, I just use small time step. Go ahead, do then combine together. You don't have accuracy. That's what I want to say here.
Okay. Thanks.
All right. Maybe we can talk more about this at the break, but I'm going to move on. Gustavo, if you're ready.
Can you see me speak?
Yep.
So I'm going to talk about the status of fully coupled simulations with CSM MOM6. This work has been done in collaboration with a lot of people from the ocean section, but also from AMP, especially Cecile Hene, CIs, Dave Bailey, Marika Holland, and also I want to acknowledge our software engineer, the main software engineer working on this, which was Mariana Wertestein. So last time I presented in the winter time, I talked about incorporating entropy fluxes into CSM MOM6. So just quickly recap the entropy fluxes definition and what we have done. So by entropy, we mean the heat associated with the mass contribution from water exchange. It can be liquid, rain, frozen, like an iceberg falling into the ocean, or vapor. And an example is if you add water in the ocean, for example, via river runoff or via precipitation, it increases the ocean mass, and therefore it can also decrease actually the ocean heat content. So the idea of adding or removing mass into the ocean has implication for heat as well. And if you now look, if you have entropy fluxes, your net heat balance at the surface will be slightly different than what you used to with the old POP model or models that use a virtual solid flux, in which the net flux will be the radiated component, short wave, long wave, then the latent heat, sensible heat, the heat associated with with the heat due to ice formation or melting, and then finally the last term, which is the enthalpy fluxes. In CSM 6, the enthalpy fluxes are now computed in the mediator. Yesterday, in the software engineer talk, we saw that we're now moving to the CMIPS framework as our default mediator. So we've implemented the option to compute enthalpy fluxes in the CMIPS mediator, which is then transferred to the different components. The way we have defined at this time the enthalpy fluxes are as follows. For liquid in green, and they all follow the same idea of is a temperature times a mass times the heat capacity. I'm using the seawater heat capacity, whether the seawater versus the freshwater is the right one. We haven't decided. We are using the seawater at this time. But for liquid components, we compute the maximum between the sea surface temperature and 0. And what we are doing is, because the other components are not providing the temperature associated with the mass whose enthalpy we are calculating, we need to guess that temperature. And that's why we apply these limiters. So in the case of liquid mass, we apply a maximum, so the max SST 0. For frozen, we do a minimum between SST and 0. And then a vapor, it comes at SST, we don't apply any limiter. So that's what we are doing right now. Again, once the other components start providing a temperature, we will just substitute the temperature, this mean SST 0, for example, to the actual temperature that the mass is coming. To show how this is adds to the balance, to the heat balance after our 100-year run in fully coupled mode, I'm showing you the net heat budget from the mediator. So the mediator prints this table every now and then. We can ask how frequent that happens. So I'm showing the net heat budget after 100 years. I want you to pay attention to the new terms, which are the enthalpy terms. There's 6 of them here on the left. And notice that only the ocean column has non-zero values at this time. And you can get an idea of the magnitude. This is in watts per meter square. So the two dominant terms are rain and evaporation, followed by the liquid runoff. So the rain and evaporation are ordered 2-ish watts per meter square. And then if you sum all these terms, it's being added into the sensible heat for the atmosphere model. So it shows up here in the sum of the sensible heat. And that's what we do as a short-term fixer, because the other components are not accounting for the enthalpy fluxes. And to accommodate for that, right now, we are just using this what we call fixer. Basically, we do the area integral of the sum of all these terms, and then divided by the total area of the Earth, and we added that value into the sensible heat that's sent to the atmosphere. And lastly, if you look at the bottom of the last column here, which shows the sum of all the heat components, we get a value of approximately 10 to the minus 3, which is pretty good. So we are conserving heat. I've shown on the table the magnitude of the global mean of these terms, but I think it's also instructive to look at maps of these different terms. So I'm now doing a 30-year average, and I want to highlight, for example, although the liquid runoff mean is relatively small, approximately 0.4 watts per meter square, locally it can be very, very large. It can be up to 245 watts per meter square, and that's in a point right outside the Amazon River where the mouse is. On average, if we sum all the terms, again, what dominates is precipitation and evaporation. They are smaller than on the mean, but they cover a much larger area than, for example, the liquid runoff, which is just outside the big rivers. So the point here is that even though globally these terms can be small, like locally can be big, some of them can be very, very large. Now moving to the fully coupled simulations that we have done. So we're using the pre-industrial control. The components are MOM6, CAM6, finite volume, size 5, CLM 5, the community ice sheet model version 2, which is no evolve, so it doesn't change the shape of the ice sheets. And then the runoff model is Mozart. I'm showing now the ocean model configuration. So on the middle panel, we have POP, and on the right, we have MOM. This table appeared yesterday on Frank's talk, and we've shown before, just to highlight the difference between the two models. I'm going to go quickly over the main differences. So you have a slightly higher resolution grid with MOM6, is a 2/3 of degree in comparison with a nominal 1 degree in POP. We are using two different coordinate systems in MOM. We're using a Z-star with 65 levels, and also a hybrid between Z-star and isopycnal with 75 levels. In terms of vertical mixing, we're using KPP via CV mix, while the fully coupled simulations with POP also have the Langmuir mixing enabled. We do have the ability to turn on the Langmuir mixing when coupling with a wave model, and that's something that Alper, Bill Large, and myself are working on in conjunction with Brandon Heiko at GFGL. We'll present in a later date the results with that, but I just want to highlight that that option is already present in MOM6. In terms of GM and ready, we're using a Mickey geometric framework to prescribe the coefficients. Horizontal viscosity is done through the isotropic Laplacian with the biharmonic, also via Mickey scheme. We have solar penetration using the Manitza scheme. And at this time, we are providing a climatology chlorophyll, while in POP, that is done with the Oman 2003 scheme, and it's using a prognostic chlorophyll scheme. And I won't go onto the advection, you can read it yourself. Okay, so now going into the experiments, I'm going to present 3 different experiments, 2 of which have the same vertical coordinate, Z-star, so it's what we call BMOM Z-star, and then in green is the BMOM GM tuning Z-star, which was done at a later time. So we first performed the 2 experiments on the top, one with Z-star, other one with hybrid, and then looking at results, we decided to do a tuning simulation where we tune the GM coefficient to improve the ACC transport, as I will show in a second. All of the simulations we did a tuning in CAM to lower the rest OM. So we play with this club gamma coefficient. We set it to a smaller value than the default value. And then in the BMOM GM tuning Z-star scheme, we play with the geometric alpha parameter. So the GM coefficients we thought were too low on the out-of-the-box configuration. So we increased this alpha parameter to 0.1 compared to the default value of 0.07 and to get larger kappa GM values. Moving to the results, we're looking at now a global mean temperature and salinity plot. So starting with the ocean potential temperature throughout the entire simulations, those are time series. In red, we have the results from POP, pre-industrial control as well. And just to highlight that the POP has been initialized, the ocean and sea ice have been initialized from previously spun up simulations as described in Gokhan's paper from 2020. So that's why there is a difference between the two.